Chapter 1, Section 2, working on the formal definition of limits. And we are going to be working with two Greek letters. This is lowercase delta and lowercase epsilon. So it's kind of nice to know what the Greek name is for those. So in this, we are working with inputs and outputs to a limit to help decide how close our answer will be to a certain value. So the limit of a function is the height, or the y value, that we would expect when we get a certain degree closeness to the x value. So here is our x value, you know, and like when we write the word limit as x approaches c of some function, well, the closer I get to c, will help indicate the closeness I am on my final outcome. So my input, getting close to c for an x value, will determine the outcome. And here's my x value of c. Well, if I were right in here, traveling up, where does it strike my line, my curve right there? And then I come over here. Well, I'm somewhat close to the expected L value, but I'm definitely not right on the L value, or the limit. So we have this notion of epsilon and delta. And if I'm within a certain delta value of c, so if I took c and added some delta, it would bring me over to what is showing up as this green line. And then I could expect the outcome to be right here, a certain distance from my actual limit, the red line. And so this limit, since I'm below, is a limit minus a certain variance called epsilon. And mainly what we're going to do is we're going to control this output. We're going to look to see how close do we want to be on the output to help determine then how close must we be to C, or how big of delta can we allow. So you actually kind of work from backwards forwards. You could go on Desmos. They have a real nice computer-aided model here showing the same thing. If I wanted to move my x value, let's throw x at there, and then controlling our epsilon. Where's my L? There. The limit would be right around 2. And if I want my output to be in the purple region here, well, then what I'm going to have to do is narrow. Here's my c value as x approaches c. I need to narrow this down so that when I input, whoops, I want to leave that epsilon alone. Okay, so what we need to do is adjust our delta and bring it in smaller, 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 so that it matches up with the two values of the purple region. So now you can see I need to be really fairly close to this c value. There's not a lot of tolerance between c and this endpoint, so c plus some delta has to be really quite small. So what delta must I choose? And that's where we're headed today to talk about that. This is a very kind of abstract idea and takes some concentrating. So here's the definition of a limit. This is what we would formally call the definition of a limit. Let f be a function defined on an open interval containing c, except possibly not c itself, and let L be the real number, the limit value. So the statement goes like this: the limit as x approaches c of some function equals L, and this is the limit value that we approach, or that we come out with, right? Our output. And that means that for every epsilon greater than 0, there exists some delta greater than 0, such that if the absolute value of x minus c is greater than 0 but less than delta, then the absolute value of the function minus the limit is less than epsilon. And this is talking about our output numbers. And then this is selecting an input x value that is delta away from C. And we have an example going on before right here, but I think we'll pass over that. I've been demonstrating it on that Desmos as well as the first page. So let's just get into problem A here. Problem A, given the limit x as it goes to 3 of 2x minus 1 is equal to some value, and we'll be able to calculate that, find delta such that the absolute value of 2x minus 1 minus 5 is less than 0.01 whenever delta is less than, or delta is greater than, the difference between x minus 3. So where do we go? Well, if I plug in 3 to this, I get 2 times 3 minus 1. I can find the limit value. It would be a limit of 5, wouldn't it? So this is my limit value, L. And what I want to do is I want to determine delta. How far away from x approaching 3 must I be in order to be within 0.01 of 5, my limit value? What we're going to do is we're going to start with this absolute value equation right here and do a little bit of algebraic work, trying to get it to look like an x minus 3. If I can achieve that, then I'll know my delta. So a little bit of work here inside. The -1 and the -5 make -6 is less than 0.001. I can factor a 2 from that. And then we can pull the 2 out front of the absolute values. It'll come out as a positive 2. Now let's divide by 2. And I get absolute value of x minus 3 is less than 0.0005. But interesting, this matches what I need for discussing delta. I now have like x minus c, where c was 3. As I approach 3, see here, as x approaches this c value of 3, I need to be within a certain distance. So this is going to look like, if I select my delta to be 0.0005, I can ensure that my output will be within 0.01 of the limit 5. So my delta I need to select is 0.0005. Letter B, assuming the limit as x goes to 1 of 6x plus 4 is equal to something, and that we have an epsilon 0.001, find delta. So if I put in 1, I get 6 plus 4, I get a limit value of 10. And just think about a linear function, 1, 2, 3, 4. With a slope of 6 means I'm going up 6 over 1. So I increase by 6 more. That brings me to a 10. This point would be 1 comma 10 on my path of this linear function. So when I approach 1 from either the left or the right, I see that I'm coming into a height of 10. Let me put this back on. Let's draw that linear function. And here is 10, which is really our limit. I want to be 0.001 from that. So that means I could be at a height of 10.001 or 9.999 if I subtracted the 0.001. That's my bandwidth that I want to maintain which implies then here is C being 1. Now where do I have to be on either side of C at 1 to ensure an output that ranges between 10.001 and 9.999? What is the delta range here? Okay, so that's what we're going to try and solve. We're going to start with our output first, and it goes f of x minus L. So my f of x is 6x plus 4 minus my limit, my L value is 10 minus 10. So y minus 10 is what that's saying is less than epsilon. Epsilon was given to us as 1/1000th, so 0.001. And I want to find that. So if this is true, if I choose an x that makes that happen, then that will give me an x minus c value, and my c is 1. X minus 1 will end up being less than delta. How close must x be to 1 to be in this range? So let's take and start with this outcome. 6x plus 4 minus 10 is less than 0.001. That means 6x minus 6 is less than 0.001. Factor out a 6, that gives us x minus 1, absolute valued. Factor the 6 out, it comes out as a positive. And then we're going to take and divide by both sides by 6. So now what I need to do is I need to divide 0.001 by 6, and here's my calculator. Notice this output here. On the calculator, e to the negative 4 is scientific notation. I need to move this 3 and one more, 4 decimal places to the left. So that's going to turn out to have 3 zeros, 0.0001, and repeating 6. All right, what we've transformed this into is what we were after for our delta. I have absolute value of x minus 1. Yep, got that. Is less than this numeric value. Well, then I just figured out what my delta must be. Delta must be 0.00017, you could say, in order to achieve an output that is within a certain distance of 10. Mainly, it's 1/1000th from that limit value of 10. A more general case, sometimes they don't specify what E is. So we're just going to find E and then put that delta in terms of E. So we're still going to start with the output here. So the absolute value, well, let's write down f of x would be 3x minus 2. There's my function. My c value is what I'm approaching to as a limit. That's 2. The limit is the outcome. When I plug in 2, I get 2 times 3 is 6 minus 2 makes 4. So my limit value is 4. And in this case, my epsilon is going to be just epsilon. I don't have a numeric value to attach to it. So I'm going to write down absolute value of f of x minus L. So f of x is 3x minus 2 minus my L value of 4. So this is saying some y minus the limit value of 4 has a certain closeness. I want it to be defined as less than epsilon. If that happens, then I can be assured that I was a certain degree close to my C value of 2. So my X I selected is a closeness to 2, and it has to be within delta distance. Okay. A little bit of algebra over on this side. 3x minus 6 less than epsilon. Factor a 3 out, It can come all the way out of the absolute value as a positive. And then absolute value of x minus 2 is less than epsilon divided by 3. Notice this is a nice matchup. Epsilon minus 2 is less than delta. Well, then delta must be equal to epsilon divided by 3. Remember, epsilon is the closeness I want to be to my L value, so that if I add L plus epsilon, I get my upper Y value, tolerance, and then if I subtract it, I get my lower Y value, tolerant, L minus epsilon. And depending on how wide that epsilon is, it dictates my selection for the X value, how close I must be to X. It'll be epsilon divided by 3. Okay, this slide's out of place. This really moves on to day 2. The graph of f of x equals x squared minus 1 is quadratic, shown to the right. And find a delta such that if delta is greater than the absolute value of x minus 2, so here's our 2, isn't it, right here. I want to be a certain distance on either side of this, delta above, and subtract delta to get the lower. Then I can get in a certain range where I can expect my output to be 3.2 or between 3.2 and 2.8, because my epsilon tolerance is going to be 0.2. So the limit as x approaches 2, and I get that off of this, because remember this format will be an x minus c is less than delta, and my c value then is 2. Here's my function, f of x is x squared minus 1 will equal some limit. Let's try substitution, and we'd have 2 squared minus 1 gives us 4, 3. There's our limit value of 3, and that is L. So I have all these things picked out. L equals 3, C is a 2, f of x equals x squared minus 1, and my epsilon is 0.2, which I got right from there. Maybe it helps you to keep track of that stuff off to the side of what the values are. All right, let's go in and write f of x minus L. So x squared minus 1 minus the targeted y value of 3, which is our L limit, is less than epsilon 0.02. When the absolute value of x minus 2, x minus c, here's my c value of 2, is less than a certain delta. Well, what is delta? Well, let's calculate out this. So a little bit of work inside. X squared minus 4 is less than 0.2. That means I could write this less than 0.2. And what I did is I removed my absolute value, because this is like the center and I have to be 0.2 away, so I can either be 0.2 on the above side or 0.2 on the below side of my centering value here. Now let's add 4 to each of these sides, and this will give me 3.8 less than x squared less than 4.2 square root and I am going to keep the square root of 4 plus 2, because it'll go into my absolute value sign here and give me a certain distance away. So that should be my epsilon, shouldn't it? Okay, what I need to do is I need to get this to look like x minus 2, right? So that will be, let's just subtract 2 from everywhere. And square root Now this will look like, and we could get this as a decimal. And I just put it in the calculator. Square root of 4.2 minus 2 gives us a delta of 0.049. So my delta will be 0.049. Okay. This is just review. The limit as we approach C from the left, and C happens to be -1, so I could rewrite this as the limit as x approaches -1 from the left side of f of x, the picture shown. From the left side, as I come into -1, it looks like we have a height of 1. As I come into -1 from the right side, I am at a height of 2, right in here. And that means the limit as we approach -1, well, the left side was 1, the right side was 2. This would be D and E because the left does not agree with the right. F of -1 would equal where the dot is, and that is at 0. There's my solid dot showing F of -1. I'm going to go ahead and skip this next one for time's sake. Here is the assignment. So please work on that.